Hello, everyone, and welcome. Welcome to the 4th annual Moon Night event that tonight is taking place virtually at the Open University. This is one of our flagship public engagement and outreach event that many of you probably remember coming on campus and actually taking part in lots of hands-on activities. But of course, we live in some interesting times and we are unable to welcome you on campus. But in some sense, actually, we are reaching out many more of you than we would have been able to if we had to come on campus because we were limited by numbers. So tonight, let me extend a very warm welcome to all of you who are joining us from around the world. And I'm aware because there are lots of my school friends, and I'm going back many, many years now here. They're all joining us from my hometown in India with their children who are interested in learning more about the moon. I know my friends who are also in China and Japan who told me that they would be joining us for this event. So wherever you are, welcome. So before I actually hand you over to my colleague, Dr. Natalie Starkey, who is going to give you the rest of the program for this evening, I thought it is worthwhile to give you a little bit of background about how actually the Moon Night came about and what we are trying to achieve here. So the Moon Night is started about 4 years ago, where many of us who actually have been involved at the Open University in working with lots of other planetary bodies. So we have always been involved in various space missions and we do all lots of fancy science. But what we weren't doing was we weren't actually sharing that excitement, or we weren't able to share as much excitement as we wanted to with people who didn't know probably as much as we knew. So we decided to actually start an annual event sometime in December, and I'll tell you why we chose tonight's date. It's a very special one, and we use this annual event to actually share all the findings, all the research that is actually taking place at the Open University about the moon, using the moon rocks, some of the moon rocks that actually were collected by the Apollo astronauts. And I know tonight in our audience we have some special guests who were able to take part in a project that we ran in their school recently. So hopefully they will be actually able to relate a bit more what we are about to present to you. But coming back to the moon, what I find very exciting is when I was growing up in India, when I was, maybe 10-year-old, I knew nothing about the moon except that I could see it in the night sky. And it always fascinated me. And the thing that fascinated me most about the moon was when I was looking at the moon when I was in India, and I was thinking, if somebody in America is looking at the moon at the same time, could we actually talk to each other without actually traveling from India to United States? And it was just those kind of, thoughts that occurred because I could see the moon in the night sky. And I didn't know that actually one day I would be doing research on the moon, on the very rocks that were brought back by Apollo astronauts. So I feel very, very, very lucky. If I can't use many varies there because I really am super lucky and fortunate. But also, these are very exciting times. As you would have heard, that there are lots of countries now interested in going to the moon. And you might wonder why. And the scientific importance of the moon, we just cannot list enough of them. And you will hear some of those in the rest of the evening's program. But the big thing that has happened in the last few years is the discovery of water at the moon. And in fact, that is what is exciting many of the scientists and actually many of the explorers around the world, because the moon, if it has water and if that water can be used to support the future space exploration, then it is going to be a game changer. And in fact, that is probably the single biggest reason why so many space agencies and even private explorers want to go to the moon. And as I speak to you, there is a Chinese mission called Chang'e 5 that you might have heard in the news. It is on its way back to Earth after having collected a large number of lunar samples that we scientists are eagerly awaiting to get our hands on, so that we can unlock many more mysteries of the moon that it is still, conceals from us. And I told you right at the start that tonight is a very special anniversary. Lunar samples that we scientists are eagerly awaiting to get our hands on. Okay, sorry, I am getting some feedback. So now it has gone away. I was just telling you why tonight is a special one, because 48 years ago, the last of the Apollo missions, the Apollo 17, actually was launched. And that was the last crewed mission that actually visited the moon and collected a large amounts of samples that we are still actually studying today. So without further ado, I'm not going to take all the limelight, but actually I'm always so excited to talk to anybody about the moon that I can't stop myself, but I must stop myself and hand you over to my colleague, Natalie, who is going to tell you more about what's happening later tonight. So Natalie, over to you.
Thank you, Mahesh, and good evening, everyone. If you're in the UK, it's a very cold day today, a very cold evening, so I hope you're snuggled up safely, warm at home, and you can join us for all the events we've got planned tonight. So as Mahesh said, I'm Natalie. I'm a space science writer, and I'm a public engagement officer here at the Open University. Now, as Mahesh said, in recent years, Moon Night has run as a sellout event at our campus in Milton Keynes, where we usually have lectures and hands-on activities, where visitors even get to hold a piece of the moon, and we even have planetarium shows. But this year, as we know, things have looked a little bit different. Now, whilst we're sad we can't open our doors to the public right now, we decided instead to have a series of events online. And so the advantage here is that we get to meet many more of you, and we're delighted you've joined us tonight. Now, in November, we worked really closely with Cold Harbour Primary School in Milton Keynes, running lots of fun moon-related events in the classroom with them. We know some of them are joining us tonight, so welcome to all of you. We're really excited to have you here, and I expect you might be able to give some of our lunar scientists a run for their money because you've learned so much about the moon recently. Now, shortly, you're going to meet Dr. Hannah Sargent, who's one of our lunar researchers here at the Open University. She's going to take us on an exciting mission to the moon using Google Moon. So this is just like Google Earth that you might use to plan a trip around the UK or wherever you're planning to go, except it's on the moon. She's going to show us the features on the moon in closer detail, as well as the Apollo landing sites, including Apollo 17, where we last sent astronauts. Now, after that, I'll be back with a team of our lunar scientists for a live Q&A. And if you have any questions for our team, then please do send them in. We've had a few already. Now, you might be wondering how the moon was formed or even what it's made from. It's not cheese, by the way, but we can tell you more about that later. What about the people who have visited the moon, or maybe how long it takes them to get there? Our team are ready to answer your questions. So if you have a question, then please email us at STEM, that's STEM, communications@open.ac.uk. After the live Q&A, Hannah will be back for a repeat showing of the Google Moon event, so do tell your friends to join us later if they aren't here now. And we're streaming live on OU STEM, YouTube and Stadium. Now, this is only the first of 3 Moon Night events this week. Tomorrow, we actually have a talk by Dr. Jessica Barnes, zooming in from Arizona, talking to us about water on the moon. And on Wednesday, we have the 6th annual Colin Pillinger Memorial event with a talk by Dr. Andy Spry about planetary protection, followed by a Q&A. You can find more information about these events on the OU STEM website, and recordings of all these events will appear on the OU STEM YouTube account soon. So in case your friends have missed them, they can catch up. Now, I'm soon going to be handing over to Hannah to take us on a tour of the moon. But first, I'm actually going to ask you all a question, and I'm going to come back later to reveal the answer. So the first question I'm going to put to you, to get you thinking a little bit more about the moon, is, does the moon rotate? So the answer is either yes or no. So have a little think about that, and maybe you might find the answer soon. If not, I will be back to tell you more. Over to you, Hannah.
Thank you, Natalie. Hi, everybody, and good evening. So my name is Hannah. I am a lunar scientist at the Open University, and I'm involved in the hunt for water on the moon. So quite recently, I was working on an experiment that we hope to perform on the moon in a few years' time using the PROSPER instrument, which is in development at the Open University. And what we're hoping to do is to actually take dry moon rock and turn it into water using a chemical reaction. Or I'm also interested in finding water on the moon that's already there. So we think there could be frozen water in the polar regions. So what we're hoping to do is use lots of different missions in the coming years to find water or make water. And that's because water is one of the most critical things that we can use on the moon. We can use it to support our astronauts, to keep them fed and hydrated. And also water is made up of hydrogen and oxygen, which is critical for rocket fuel, which means we could actually launch more missions from the surface of the moon. Now, I didn't actually know that this was going to be my career. It's nothing you can almost plan for. I actually started off studying science in school and being a physicist. And then I came across this course where I learned all about space exploration. I didn't realise it was something that the UK was involved in. And from there, it just lit a fire inside of me, and I've just been pursuing that ever since. And it's really exciting to now be a part of the lunar science community here in the UK. So what I'm going to do now is walk you through how you can explore the moon from the comfort of your own home. So there's actually so much you can access for free, even though we can't get out and explore ourselves right now and go and visit to museums or the university. So using some free software, you can follow along at home, or you can have a go later, but I'm looking forward to seeing what you might find. So here's something I recorded earlier to help you explore the moon. Okay, so to begin with, I'm going to be looking at Google Earth and an aspect of that called Google Moon. Now, many of you might be familiar with Google Earth. You can access it on your internet browser, or you can actually download for free something called Google Earth Pro, which is what I'm going to be using today. I just find it easier to work with. So if you go to this is just the opening screen of Google Earth Pro. And if you look to the top bar here, you might notice there's a small icon in the shape of a planet. And if you click on that, you can scroll down to Moon, and that will take you to Google Moon. Now, Google Moon was created about 10 years ago now to celebrate the 40th anniversary of the Apollo 11 landings. So Google Moon uses imagery from Clementine, and this took images of the moon in orbit, and that's why we have these stripy images, because as the satellite was moving up and around and across the surface of the moon, and around the moon, the lighting would have changed slightly throughout the days, and that's why you have these different sort of stripy artifacts of these images. And this is the face of the moon that you might be used to seeing. So this side of the moon, called the near side, is always facing Earth. So when you look up into the night sky, this is the side of the moon that we always see. So you might be used to seeing some darker areas and some lighter areas. So the lighter areas, we call them the Highlands. These are older materials formed when the moon initially, when it was sort of molten rock, when it was initially cooled down. This is some of the first material to cool. But then in the lower areas, these actually flooded with lava in these oceans of lava, and forming this basaltic darker rock. And actually we call them the mare regions, which translates to seas, because ancient astronomers actually thought that these were seas on the moon. But what's interesting, if we turn the moon around, this is what we call the far side of the moon. So very few people will have seen this with their own eyes. Only the astronauts that have orbited around the moon will have seen this side of the moon themselves. And you can see it's very different, actually. It's a lot of lighter material, so a lot of highlands on the far side of the moon. And it's not called the dark side, so that's a common misconception, because the far side of the moon also sees sunlight. And that's why we were able to take these lovely images across the surface of the moon. Okay, so let's scroll back around here also. Okay, now one of the main reasons I like to use Google Moon is because it's good for looking back in history and human exploration, particularly during the Apollo missions and so on. So, for example, let's take a look at some historic maps. So on the left-hand side down here, if I click on historic maps, so these are maps that were created around the time of the Apollo missions to help support the missions. So we have some geologic charts here, and they're split up, I believe they're called quadrangles. So each map would have, just to break it down into sort of bite-sized chunks. And if you click on it and zoom in, oh, sorry, see if I can click on one of these. There we go. Explore this map. So you can actually look at the original map that was created, and if you use your scroll wheel on your mouse, I would suggest using a mouse for these. I just find it easier to work with. So these are some pretty old maps here. This one was created in 1960, in fact. So this would have been used using images of the moon, and they would have looked at the different shades on the surface and the shapes that they could see and try and determine what sort of materials they are. And again, you can look further at those over there. But more importantly, these maps are used to help determine safe landing sites as well. So you can use the geologic maps to help find areas of particular interest where we might want to collect some samples to bring back and study here on Earth. We also have topographic charts. So these are charts that tell you about how steep slopes are and what the terrain is like. And this is helpful for finding your safe landing site, because you want to land somewhere nice and flat. It's really hard to pinpoint an exact place where you're going to land. So you need to have a big, wide open space, a flat space that is safe for the astronauts to land in. Okay, so I'll close off of the historic charts. Now, you might also notice these small red flags, and those little red flags are human artifacts. So these are things on the moon that were created by humans. And we also have the Apollo mission. So what I'm going to do, I'm going to take us in to Apollo 11. So I'm just going to click on the Apollo 11 badge here, and it will take us all the way in. So you don't need to know where exactly the missions went, because Google Moon will do it for you. Okay, so what we've got here is the landing site of Apollo 11. Overlaid on top is one of the maps that was created showing where the astronauts went. So you can see they didn't explore too far away from their landing site. Just a couple of little craters nearby, nice and close to their lander. So if you zoom in, so I'm just going to scroll in here, you can see they've superimposed the lander. Let's see if I can turn around. So we have our lander here, we have a flag here, and you can see there's lots of little things you can click on. So there are some YouTube videos that you can go and check out, of videos that were recorded on the surface. We can see exactly where things were placed. So we have SWC, this is our solar wind collector. And we can also check out some cool images that were taken on the surface. So if I go the view from Little West Crater, fly to this photo. So this was taken by one of the astronauts. You can see we've got the lander here. There's our solar wind collector. This is one of the science experiments. Got the nice shadow of the astronaut there. And this is one of the craters near to the landing site. Okay, so if I zoom out, so there's lots to explore here, lots of like cool little artifacts to go and check out. But now I want to take us on to Apollo 17. So this is the last mission from the Apollo era. So these were going to be the last humans on the moon, and we can see how different the missions were. So I'm going to fly us in to the Apollo 17 landing site. Okay, and you can see so we've got superimposed here the route that the astronauts took, and so they had a rover this time so they could go and drive around and explore, and you can see they explored much further away from their landing site than they did in the first mission to the moon in Apollo 11. Now what I'm going to do, one of the cool features they have here, they have some guided tours from the astronauts, so you can listen to Buzz Aldrin talk about Apollo 11. I'm going to give you a quick snippet of the Harrison Schmidt guided tour. So Harrison Schmidt was the only scientist to have ever gone to the moon. Everyone else, they were, you know, your pilots, the standard astronaut of the day. Whereas having a scientist, particularly a geologist, is really helpful because they can pinpoint areas of interest or particular samples on the surface with their eyes that we might not have thought about or identified from orbital images. So let's have a quick listen to this tour.
I'm Jack, Apollo 7, flew on the Apollo 17 mission in December of 1972. The crew of Apollo 17 was an aggregate of two backup crews, Apollo 14 and 15. I replaced Joe Engle on that crew, and Gene Cernan would be the commander, and Ron Evans was going to continue as the command module pilot. Gene Cernan got out of the spacecraft first, and I followed him fairly quickly afterwards. We were in a valley deeper than the Grand Canyon of the Colorado. The mountains on either side were 2,100 meters, or about 7,000 feet high. The sun was as brilliant as any sun that you can imagine. Even more impressive was the Earth, which was hanging over one of the mountains and stayed hanging over that mountain, the South Massif. And that was really a magnificent sight for me, and that's what I remember as being sort of my first real impressions of the Valley of Taurus-Littrow.
Okay, so there's plenty more for you to check out there. I'm just going to exit this ground level view, and I want to take us to one of the places they visited. So they visited the base of this mountain here, the South Massif. And you can see that the images, the problem with the Clementine images is that they are outdated now. We do have much more improved imagery, so there isn't a lot of resolution here. But I do like that they have superimposed some images taken at these locations that you can go and zoom in on. Let's see. Fly into this photo here. So this is at the base of the North Massif. There's another of the crew members there, likely taking some samples. Oh no, sorry, taking photos and images by the looks of things, and videos. There's the rover down there. You can see their footsteps in the sand, well, in the soil, shall I say. Okay, so I'm just going to zoom out of this now. So what I'd like to do next is look at this same location, but using a different piece of software or program that you can all have access to. Okay, so next I want to take you to use another piece of free software. Well, it's a program that is available online, and it's called Elbrock Quick Map. So if you search into your search bar, Elbrock Quick Map, this is what should come up. Okay, so Elbrock Quick Map is actually, it was designed for the Lunar Reconnaissance Orbiter camera team. So the Lunar Reconnaissance Orbiter is actually in orbit still around the moon, taking lots of images using all of the different cameras, and also obtaining lots of different information using other instruments they have on board. But the team wanted to be able to see their images as one on the moon and look at kind of like how they refer to each other and kind of like the context within the whole moon. And so they worked with ACT to develop this program, and most importantly, they made it free to use for everyone, which has been great for people like me I've actually used this in previous research, but even just for lunar enthusiasts who want to go and explore the moon and looking at some of the most recent images and data that we have available. So first off, it shows you this 2D version of the moon, but you can see it's beautiful and crisp. I find a lot easier to look at than the Google Moon version, and you can actually switch to 3D and take a look again all over the moon, and it is just, well, I find stunning anyway. So I'm going to return us back to the home view, and I want to fly us in to the Apollo 17 landing site again. So it's actually been around 48 years, almost I think to the week, since the Apollo 17 mission, which is one of the reasons why I'm really interested in taking a look at this site again. And we can take a look at this site. So first off, how do we find it? It can be a bit overwhelming, so there are a lot of different options here of layers of things to search for, but I'll try and walk you through it gently. So if we go to overlays, and we can click on anthropogenic features. That's just a fancy way of saying human artifacts. So things that humans have created that are now on the moon, whether that's landers or rovers or debris or whatever it is. And if you click on the text underneath, you should see there's a lot more information and directions of where to find more information. And we can actually narrow down the particular feature that we're interested in. So I'm going to look for Apollo 17, but you'll see that there are lots of other missions highlighted here from lots of different countries as well, which is really important. So first off, I'm just going to take a look at Apollo 17. So I want to head to the Lunar module. It takes us right in, which is perfect. Okay, so I just want to check. Okay, so I'm currently in 3D, but for what I'm about to do, I want to be just on the near side projection. Okay, so it doesn't work as well with 3D. And what I want to do, if I zoom in here, okay, I want to now draw a shape around the Apollo 17 landing site and search for the best high resolution images we can find. So I'm going to draw a polygon, just a shape around here, double click to finish, and I'm going to search for, again, lots of different data sets you could look at, but I'm interested in the narrow angle camera. So this is the highest resolution images that we can look at, but it will give you a lot of, it will just kind of, your screen will freak out. So we want to filter it down. There are lots of things you can look at, but for what we're doing here, the only thing of importance is resolution. So you want to have the smallest amount of space per pixel. So I want to go less than a meter per pixel. Okay, and I'll click on the first one that comes up and it will load, and look at that. So if I zoom in, I think this is the maximum I can zoom in. So this here is the lander, so it's still there. What's left of the lander on the moon, we've got the little shadow created from the lander, and then you can see all of these marks from where the crew in their rover went and explored. So these are images that have been taken from the Lunar Reconnaissance Orbiter every time it flies over the Apollo 17 landing site. So these are taken at different times of day. So no claims of we haven't landed on the moon before here. So we've got all of our lovely images here from the Apollo 17 landing site, lovely and crisp and really beautiful to look at. But next I want to take us back to, so if you remember, we were looking at, or the team went to explore the North Massif, which is this area here. So they explored up to this region. And if we zoom in, even with the wide angle camera, which is what these base images are here, the resolution is so incredible, even compared to the Clementine images. You can see these boulder tracks of boulders that have rolled down the slopes of the moon, and these are created when rock is broken off or ejected from craters, from impacts, meteorites striking the surface and so on. And so quite often we find these boulder tracks down slopes on the moon, and the Apollo 17 crew actually went and visited one of these boulder tracks. And what I'll do is I'm hold on, actually no, what I'll do is I'll show you here. I'll try and superimpose it. Oh, go on, I'll have a look. Brief look at this particular boulder. NAC images. Let's go to high resolution. There we go. So you can see that this boulder was actually broken in half. It stopped rolling and it had fractured and crumbled. And the crew visited this site, and you can see these little dark squiggles right next to the boulder. And this is where the crew were walking around and taking pictures. And the rover actually pulled up quite close, I believe. So we actually have a picture of the crew that was taken right next to this boulder. And in the work that I've been doing in the past, we've actually been looking at boulder tracks on the moon, and we can use these images. So we've used Quick Map to measure the size of the boulders, the size of the tracks and the shadows within the tracks to try and understand how deep they are. And we can use that to better understand how soft the surface material is. And if we can do that at locations that we haven't visited on the moon before, and make sure that any rovers that we send there aren't just going to sink into the soil irretrievably. So it's really important that we can use these images for free to do some really important science. Okay, so let's exit out of here. Let's delete these. So now I just want to show you one of the features of Quick Map that I really enjoy, and that is looking at the moon in 3D. Now, because they have some of the highest resolution images and the most up-to-date topography maps, so that, again, I mentioned earlier, they are, the slopes that you see on the moon, on the hills and in the craters. And what they've done is they've overlaid them together. So in 3D mode, you can explore them with sort of an astronaut's viewpoint. So if we just briefly switch our projection to 3D mode, it can take some time for the images to load, because it's a lot of information that it's now handling. Let's see. There we go. So you can zoom in and out, but if you hold down the mouse wheel, you can take a look. So this is what the astronauts would have seen as they would have descended towards the surface of the moon. So as they were flying in, they would have had to make sure that they landed safely in a nice flat area. And you can zoom in and take a look. So if you were to explore at the base of the mountains, this is what you would see. And looking behind you over here, and eventually the images to catch up. And this is a really useful tool if this sort of program can be used to help train astronauts as they plan their routes, as they go and collect samples and do experiments on the moon. Okay, so now I'm just going to exit out of this. So some of you might be aware that very recently, let's go back to the 3D view. So very recently there was a Chinese mission to the moon, and this will be only the third country to get samples from the moon and bring them home again. So this is going to be a robotic mission. It's the Chang'e 5 mission. And it's heading to a northwest region of the moon, somewhere up here. And they're going to be collecting samples and bringing them home. And one of the reasons why they're interested in this particular area is because it's long been thought that volcanism on the moon, so volcanic activity, kind of died out quite early on in the moon's history. But there's reason to believe that there's some much younger material here, suggesting that volcanic activity perhaps went on even longer than we originally thought. And that opens up a lot of questions for the scientists trying to understand the moon's formation and and what's been going on in the history of the moon. So that's one really exciting thing about the mission, but also by sending missions to the moon and getting them safely home again, that's one step closer to sending humans to the moon and getting them safely home again. So a lot of this work is building up to having humans on the moon once again, but hopefully for a longer period of time. Now, next up, I want to take us to the south pole of the moon, because this is where the future of lunar exploration is really looking like it's going to be. So in the south pole of the moon, there's reason to believe, if it's on 3D it gets a bit messy, there's reason to believe that there's frozen water there, and that is going to be a very critical resource. I will talk a little bit more about that in a moment. But first off, I want to take us to Schrodinger Crater. So Schrodinger Crater, let's go to a south pole projection. So Schrodinger Crater is in a really interesting location, which makes it an interesting target for future missions, for both science and exploration. Now, Schrodinger Crater lies near to what we call the South Pole Aitken Basin, which is in this region down here. And in the South Pole Aitken Basin, there was a giant impact that released material from deep within the moon and ejected it onto the surface, including probably in Schrodinger Crater. So if we can sample some of those materials, we can learn about what the interior of the moon is made of. Now, Schrodinger Crater itself is also quite a large crater, so big that it has an inner ring. So you'll see these sort of inner rings form in quite large craters, and this is material again that has been kind of risen up from an impact, and we can sample that and learn more about the types of materials found on the moon. But also, you might have noticed this quite dark area here, and this is what we call a pyroclastic vent. And pyroclastic vents are quite cool because these are vents where hot magma has basically exploded out of this vent and it's instantly cooled into a glass. But if we can sample that glass, trapped inside could be some of the gases that is found in the material deeper within the moon. So we don't have to dig into the moon, we can just target these areas and it will tell us a lot about places that we can't access much deeper down. And one final thing of interest about Schrodinger is that because it's so close to the South Pole, the sun is very low in the sky, and when that happens you get quite large shadows, and in some places, no matter what time of day or time of year, there are shadows that are, they're constantly shadowed. There are areas that are constantly dark and cold, and what that means is that they could trap water ice because it will just stick there and instantly freeze, whereas anywhere else on the moon, water will instantly vaporize. So there are some areas, we call them permanently shadowed regions or PSRs, and these are a massive target for the future of lunar exploration. So Schrodinger could be a really interesting target, but it's still a bit far out from directly over the South Pole, and I'll kind of show you a bit more about that now. So if I go to layers, I want to look at permanently shadowed regions. So this is highlighted areas that I was just mentioning in permanent shadow. But these are, if I look at some of the information, 10 kilometers squared or larger. So these are massive permanently shadowed regions. So there are going to be some in Schrodinger as well. But there could perhaps be better targets in these larger areas here. So these kind of orange outlines were calculated looking at the slopes of the craters and the angle of the sun in the sky, and basically figuring out where there were areas that wouldn't get to see sunlight. But we can actually look at lots of different data sets from different missions and see why we're so confident that there's going to be water ice in these places. So there are areas that we know are going to be in shadow. Okay, so that's the first step. But next we can look at look at the diviner instrument. So this is looking at temperatures. So if I look at the minimum temperature, okay, and overlay that, what I'm just going to do, I'm just going to blend it in a bit so we can see. And you'll see that in these areas that we think are in permanent shadow, they tend to be the places that are really cold. In fact, some of these places are as low as 30 Kelvin. That's around minus 240 degrees C. And this is some of the coldest places in the solar system. So even though we can't have liquid water on the moon because there's no atmosphere to keep it, to stop it from vaporizing, any water that is brought, if it reaches one of these cold traps, it will instantly stick there. So over millions, billions of years, these could be places that have collected quite a lot of water that we could potentially harvest. So next up, let's take a look at, I think it's the LEND instrument. So this is looking using a neutron detector. It was able to detect hydrogen that we think is in the form of water. So the resolution isn't great. Let me just turn this down. But you can see over particularly these big PSRs, there seems to be quite an increase in the amount of hydrogen, which is telling us that there's probably water or surface water in these regions. So this is why over the next few years you might be seeing a lot of missions heading to the South Pole, because what we want to do is prove, because we haven't actually been there yet, is sample it and see if there is actually water there. And actually that's some of the missions that I'm involved in. So the PROSPER instrument is being developed at the Open University, and it's going to be landing near to one of these, hopefully near to one of these permanently shadowed regions, and drilling down into the surface and seeing how much water we think we can find there. And hopefully you'll start to see, maybe in our lifetime, permanent moon bases on the moon near to some of these PSRs, hopefully again in a flat area, because we need to be nice and safe, and utilising that frozen water to keep our astronauts alive, but also to convert that water into hydrogen and oxygen, which is our rocket fuel. So perhaps that could get our astronauts back off the surface and return them home to Earth, or even sending missions onwards to Mars. So there is a lot going on, and so yeah, keep an eye on future missions, even starting as soon as next year, in fact. Now there is so much more that you can explore with this program, and I could spend hours going over it. But what I would suggest is if you scroll down to the bottom of the screen, there's a question mark, and if you click on that and go to Lunar Examples, it will take you to another link here. And the team have spent some time showing you lots of different things that you can explore. Even just straight away here, explore Apollo 12. You can see this phenomenal image here taken at the Apollo 12 landing site. You can also chase the satellite. So this is quite a nice little demo. Quite easy. You can see where the satellite is today, and see what it's flying over and what it's taking images of. And there's just so much more you can play around with. So you could even, as a demo here, this one's slightly more complex, but you can plan your moon base. So what you do is you look at all the different the data sets and see how they combine together, and you can find places that have water, that have flat places to safely land, and multiple different scientific places of interest. And yeah, there's just plenty for you to go and explore. So I'd highly recommend if you spend some time playing around on here. Okay, so thank you everyone for taking a look with me at the moon. There's so much more in these websites for you to go and access and enjoy and discover as well. So I'm really looking forward to seeing what you might find when you check out these websites and see the moon for yourself. So thank you, and we'll show you again later for those of you who joined in late.
Hi everyone. Well, welcome back to Moon Night 2020, coming to you from the Open University. I hope you enjoyed Hannah's trip to the moon. I found it fascinating and I can't wait to go and have a go with Google Moon myself. You can have a play with the software at home or at school if you have access to a computer and the internet, and you can make your own journey around the moon and go and explore some of those amazing features. If you're just joining us and missed Hannah, then don't worry. As she said, well, she's here with us now, but she'll also be back for a repeat showing of the Fly Me to the Moon film at 6:15. Now, earlier on, if you were with us earlier, I actually posed a question to the audience, and you might be wondering if you got the answer right. So let's remind you of the question again. The question I put to you was, does the moon, I think the wrong question has come up on screen. That's going to be our question I'm going to ask you later. So it's a bit of a giveaway for the second question. I'm going to tell you the first question because you want to know the answer to that one first. So that was, does the moon rotate? Yes or no? Now, if you said yes, then well done. You got it right. So you can give yourself a big pat on the back. I'm afraid we have no prizes for you tonight. But don't worry if you got it wrong, because actually it's a common misconception about the moon that it doesn't rotate. Now, whilst the moon does spin on its axis, it completes a rotation once every 27.3 days. The confusion is caused because it actually takes roughly the same period of time for the moon to orbit around the Earth. So that means that it always keeps the same side facing us. And this leads into the whole idea of there being a dark side of the moon. Well, actually, it's not dark. It receives almost as much sunlight, I think it's the same amount of sunlight as the near side of the moon that's always lit to us. So really, we should call it the far side of the moon, not the dark side, because it does receive sunlight. But there is some confusion. It's hard to try and understand how all the objects in the solar system do orbit around each other. So that got us started with a question, but I want to know if you have any questions for our scientists, who I'll welcome in just a minute. We've had a number of questions in already, actually, and I'm going to get started with those just as soon as I let the team introduce themselves. Now, if you have a question to ask our team about the moon, then please do email us. It's on STEM, which is STEM-communications@open.ac.uk, and I will put your questions to the panel shortly. So let's get started then and meet our team of amazing lunar scientists who we've got here tonight. And we're going to start with Hannah. I know you've met her already, but we'll start with Hannah and she can reintroduce herself for those of you who have just joined us. Hi, Hannah.
Hi. So, yeah, some of you might have already heard me introduce myself earlier. So I am a lunar scientist at the Open University, and I focus on the technologies that we need to find water on the moon or make water on the moon, so that one day we can use that to help build a moon base and perhaps even support missions onwards to Mars.
And Hannah, you've just finished your PhD, haven't you? You successfully just completed your PhD, and now you're a practicing lunar scientist as such. You've gone into the big wide world and doing some real, not that your PhD wasn't real research, but you're now continuing that research. Can you tell us a little bit about that? What are you working on right now?
Yeah, so in my research, which I've just been finishing up, I was working on a technique, on a chemical reaction where you can actually use lunar material, lunar rocks, which I was lucky enough to handle, and create water from that. And that is an experiment that will be trialled on the moon, hopefully in a few years' time. And I'm now working on a rover concept called the Love Me X rover, and that is something that is hopefully going to be used to drill for water on the moon and search for water on the moon in the polar regions that we were just talking about.
That's so exciting. It must be fascinating that you are working on these amazing things. And I don't think probably many people joining us tonight probably didn't realise you can actually make water from rock. And I know it's something that I've learned from knowing about your research, and it's absolutely fascinating. I know you did a TEDx talk at the Open University. Was that last year?
Yeah, so that was last year, and that was talking about all of basically the importance of water on the moon, and how we can use it and utilize it to support these future missions. And it's all about basically making space exploration feasible, because we can't keep bringing everything we need from Earth, and we need to be able to use the local resources and local materials, so we don't have to keep sending big heavy rockets to and from the Earth.
That's fantastic. So if you want to learn more about Hannah's work, then do look for her on Twitter, and we've also got lots of information on our websites and on our Twitter page as well. We tend to share all these links. So if you want to catch up with Hannah's TEDx talk, then do, because it's a really good one, a really succinct talk. That's why I like those talks, because they're nice and short, and you get so much information. Now we're going to actually welcome Tara Hayden next. Is Tara with us now?
I am, yes. Oh, my camera's...
There we go. There she is. Hi, Tara.
Hi.
Can you tell us? Can you tell the audience a little bit about who you are and what kind of work you are doing on the moon?
Of course. So I'm Tara. I'm a PhD student at the Open University, and I work on looking for volatiles in lunar meteorites. Volatiles being like water or carbon present within these lunar meteorites, and understand how that came to be and whether it is similar or different to what we have measured in Apollo material.
Okay, so you're working on meteorites mostly, is that
yes.
right? Okay, so this means, so do you want to explain a little bit more about the difference between the Apollo samples that we have and the meteorites, because that might be a little bit misunderstood by some people?
Of course. So the Apollo samples were collected by the various astronauts when they visited the moon, and they were returned back to us and kept safe within NASA's vaults, where they kept them safe from contamination and from a lot of contact, which meant that they are pristine. So they are as they were when they were on the moon's surface, more or less. Lunar meteorites, on the other hand, have been ejected from the moon's surface, and they floated about in space, then been pulled to Earth by our gravity, and they have come through our atmosphere, and on their passing through the atmosphere, the outside of them completely melted, and then they landed in deserts. These are hot deserts, like in Northwest Africa, in the Saharan Desert, or in Antarctica, a cold desert, where they have sat for thousands or so of years before we find them on various expeditions, and then people like me get to study them and get to learn their secrets.
When you were younger, did you imagine you'd be doing this right now?
Definitely not. I could not have imagined being part of what I'm part of, and I just feel very privileged to be within this community and actually just get to hold these rocks all the time and actually learn their secrets and understand more about our solar system and our history. It's fascinating.
And I'm interested because I know everyone who works in space science particularly have a very different route that they came into space science. So what's your background? How did you get interested in studying the moon in more detail?
So I did my undergraduate degree at university, which is education beyond school, in geology. So I studied rocks from Earth, and I did this at the University of Glasgow, which meant I got to understand how rocks work, how they formed, and then in my final year I got the opportunity to study some Martian meteorites, and I found I really enjoyed working in the lab and learning the secrets about these space rocks and how similar they were to Earth rocks, but also how different they were. And so I found I really enjoyed this and looked around for different work I could do in this area, and I found a PhD project all about volatiles on the moon, and the rest is history, I guess.
That's brilliant. And I think let's just explain also what a PhD is, because some people, if we've got some of our younger viewers, they probably don't have a clue about university and things. So what stage do we do a PhD?
So you when you finish high school at age around 18 or 19, I'm not sure, you then go on to university, which is education beyond school, and you complete an undergraduate degree, and this is 3 or 4 years depending on where you study. In Scotland I studied for 4 years, but in England they tend to be about 3 years long, and at the end of this you graduate with for instance a Bachelor's of Science, and you can have the opportunity to do further study or further education in terms of a master's degree after you have finished your first degree, and then you can go on to a PhD, which is further after you graduate.
Thank you. I think, Nana, that's a really good summary, because I think when I was younger, I had no idea. I didn't know that, PhDs existed, and now I have one. So I think, wow, it's amazing that you start to learn all this stuff as you go through the school system. Thank you, Tara. We'll come back to you with some questions soon. So I think, can we have Ben next? Have we got Ben with us?
Hello.
Hello, yay, we can see you. Hi, Ben. Can you tell us a little bit about your background and what you're working on at the moment?
Yeah, of course. So my background, I'll start off with my project first, actually, and then I'll talk about my background. So I don't specifically look at lunar meteorites, but I look at meteorites that are actually older than the Earth and the Moon, and I investigate what they're made up of, their minerals, and I investigate their water contents. So it's very similar to what Tara does and everyone else at the OU does, but just on a different type of meteorite. So we're using the same techniques to look at water that was possibly present in the solar system before the moon formed. So that's sort of what I do. And I've always been interested in sort of geography, physical geography. So that's sort of where I began at GCSE. I then did geography and geology at A-level, and then I did geology at university, so similar to Tara, so looking at earth rocks. I then did a master's at the University of Portsmouth after my degree, and that was in planetary science as well, again looking at meteorites but not from the moon. And I'm now here at the Open University in my second year of my PhD, looking at these very old rocks from outer space.
That's fantastic. Thank you. What a perfect summary. And I know you a little bit, and I love that. I asked some of you once I was getting to know you about some interesting facts about your life, and I know that you're into doing art as well. Actually, you told me you did some Harry Potter art, which I think that's absolutely amazing.
Yeah. So
here we go.
In my spare time, I like to do digital art, so I like to do drawings and stuff like that on my computer. So, but obviously my main interest is space and meteorites, and I've even got my own little meteorite at home. So.
Oh, look at this! Where's that one from?
So that's just an ordinary chondrite, which is just where sort of bits of dust in space have come together and made little meteorites. So instead of forming a massive planet like the moon or Earth, instead it's just these tiny little pebbles that are out of space. So.
Fantastic. You can buy meteorites, can't you? You can buy them online.
Yeah, you can buy them on eBay. You can even buy them on Facebook if you know where to look. Some are much more expensive than others. So, for example, I look at meteorites that are very rare and very expensive. So it's about 150 per gram, which is a bit similar to Martian and lunar meteorites. And then you can have other meteorites like these, which are just ordinary chondrites, which are much, much more common and more like 90% of our collection, and they're a lot cheaper. And you can buy them in lots of different places.
There we go. That might be something for the Christmas list then.
Exactly.
Okay, so we've got one more person to meet, and that's Lucy. Are you with us, Lucy?
I am, yeah. Hello.
Excellent. Hiya.
Hiya. Can you see me?
Yeah, we've got you. Do you want to go ahead and introduce yourself, and then we can get started with some of our questions? This will be really exciting.
Brilliant. Okay, so my name's Lucy, and I'm a first year PhD student at the OU. I'm studying the origin of water in the moon, so in the actual rock. So I'll be targeting different minerals to investigate the water and the other volatiles in there. Now, I haven't actually had chance to go into the university yet. Obviously, I've started in October, so it's been a little bit strange just working from my bedroom, but I am excited to get to work on some Apollo samples, hopefully in the new year. My interest in the field started from quite a young age. I remember I've got a very vivid memory of my dad explaining to me when I was very, very small what the Milky Way was and what the constellations and the stars were, and that sort of started this interest in space for me. I also was really, really interested in the outdoors and landscapes, and I went on lots of hikes with my family as a kid. So that made me want to study geology. And like Ben and Tara, I'm also a geologist. I studied at the University of Manchester. And whilst I was there, I got really interested in the field of planetary science. So I got to work on Lunar 20 samples, which was a 1972 mission, a Soviet mission to the moon. And that just sparked my interest really in lunar research and made me want to come and study at the Open University. So that's what I'm doing. That's why I'm here. Thank you.
Thank you. No, that's fantastic. Okay, so now you've met everybody. You can see we've got a lot of geologists here who know a lot about the rocks on the moon. I too am a geologist, but I didn't come from a lunar background. I've worked on comets and asteroids and even volcanoes, so quite a mix of stuff. And I am also a geochemist by training, so I looked at the chemistry of these rocks, as many of the people here tonight are. So I'm going to get started with actually going to put Tara on the spot first, and I'm going to ask you the first question that's coming from Jack, and it's, how did the moon get to be in space? Which is a great question to get us started.
Okay, so this is well, how the moon formed, so how it actually came to be where it is today. It is thought that a Mars-sized body called Theia hit the very, very early Earth, and this is billions of years ago, around 4 billion years ago, that there was a catastrophic collision between this Mars-sized body and Earth, which blew off material from both of these bodies that went into orbit around the Earth, which eventually came together to form our moon, which has stayed within the orbit of Earth, though it has got further out than it initially was, so it is a further distance than when it initially formed 4.2 billion years ago. That's a great question.
4.2, it's very precise, isn't it? And it's, I mean, can we just explain also, this is 4,200 million years, is that correct?
That's correct.
So yeah, because sometimes we talk in billions and it doesn't really mean much, does it? It's such a long amount of time that we're talking about. So the moon, so we're talking about the solar system formed about 4.6 billion years ago, and then the moon and the Earth formed then about 4.5 billion, and then the moon formed 4.2 billion. So it's all a very long time ago.
We think on geological timescales, and we tend to forget that this is actually a very long time.
Exactly. It's crazy, isn't it? Billions of years. Okay, right. That was a great answer. So we've actually answered a question about how old is the moon from Norman and Brandon that we had in. So we know that the moon is about 4.2 billion years old. But who can we go to about this? Maybe Hannah can help us. Is all of the moon 4.2 billion? Well, we know it formed around then, but can we know from your presentation earlier that actually you talked about there being volcanoes on the moon and things. So is the whole of the moon the same age?
Oh, this is a hard question. So all of the material was there on the moon, but it's gone under a lot of changes. And so as those changes occur, that kind of sort of resets the clock a little bit. So there have been a lot of changes. So we originally had, as the original moon, and once after this impact and it all collected together into this big ball of old moon, it cooled down and it had this crust. And that's what we call the Highlands, because this is kind of the oldest material on the moon. And then in the lower regions, we had these sort of seas of lava that eventually cooled down, and they're the mare regions. But then there was other activity that happened after that with these volcanoes that were potentially going off later on. So actually, there's been a lot of changes that have been happening over the moon that resets that time clock.
Okay, that's brilliant. Okay, let's see. I've got a question maybe for Lucy, and I'm putting these scientists on the spot here. So hopefully if they can't answer the question, pass it back and we'll find someone who can. But I'm going to ask you the question, why is the moon spherical? So why is the moon round? That's a good question.
That is a good question. All I'm going to say, and all I really understand of it, is gravity. Exactly. So the inside, it's accumulated, all of the matter has accumulated around an inner body, shall we say, and it's all sort of come together. But I'm sure someone can explain that much better than me, because I'm not a physicist, so I'm going to hand it out.
Does anyone want to add to that?
I mean, I guess I'm technically a physicist, but yeah, gravity is the answer. It's just, it's always pulling things in towards the heaviest part, and as you pull things in, it gets heavier and heavier, and it's just happening in all directions, and when that happens, you form a perfect sphere.
So basically that's actually quite a good thing to talk about, because not all objects in space are round. So when we think about the planets, they're definitely all round, and then we think about many of the moons that are out there, and we know that Jupiter, for example, has 79 moons or something like that, and they're all round. But actually, when we get to the smaller objects in the solar system, the ones kind of that I've studied, like comets and asteroids, often they're not round because they're just not big enough to have pulled themselves into a round shape. So you'll find that they're very odd shapes a lot of the time. In fact, one of the missions that the Open University was involved in was the Rosetta mission to Comet 67P. And it looked a bit like a rubber duck. It was really funny. It sort of had a head and a body, because it definitely wasn't a round object. It was only about 5 kilometers across, which sounds very big, but actually in the scale of space, that's quite a small object. So yeah, round things basically have to be big enough to become round and have their gravity. Oh, I like this one from Alfie. What was the first animal to travel to the moon? Go on, Hannah.
This is one of my favourite facts, so I really have to jump in. I'm sorry. So it was some tortoises and some other little squirmy things. I believe it was a Russian mission, and they orbited the moon. So the first living things to go around the moon and see the other side of the moon were tortoises, which I think is a really fun fact.
I did not know that. That's amazing. How were they? Little ones, or
I don't know how big they are, but I remember now it was the Zond 5 mission, I believe, or something like that. Yeah. So, and I believe they were safely returned to Earth. I believe
they were.
So yeah, that's a really, really good question.
So they've not landed on the moon. So they've not actually been to the moon itself, but they've been in orbit around it.
Yes, as far as I'm aware, there haven't been animals on the moon other than humans.
Okay, brilliant. Thank you. What does the moon smell like, anybody? Let me just see who. This is from another Alfie, but a different Alfie to the one I just asked. Any idea what the moon smells like? We need to ask kind of one of the astronauts that's been there, but they would have had their suits on, so they probably wouldn't have been able to smell it anyway. Any ideas from what we know it's made of?
I mean, I believe it was gunpowder. I think that's a word that was thrown around by the astronauts. But I know it caused some people, if you sniff too much of it, it was quite irritating. So a lot of them actually got sick, almost like sneezing from breathing it in. So actually, it's not the kind of thing that you want to be smelling too much of, because the dust on the moon, as our researchers know, is quite sharp and angular, and that can get in the way and stick inside your throat. So you don't really want to be smelling it.
No, that's good. And that's partly why we need spacesuits when we go to the moon, because not only do we need air to breathe, but we have to kind of protect ourselves from that environment that is not very good for animals and humans. Okay, so next question. This is going to be definitely for Hannah again. Sorry, I know you've just answered the last one, but I know this is kind of your area. Could you grow things on the moon? And has anyone tried? And this is from Hector, age 9.
So if you were to plant a seed on the moon now and poured some water in, not a lot would happen, I'm afraid, because the seeds and plants need an atmosphere, so air, to grow in. So what we'd have to do is build a completely contained greenhouse, basically. So we could grow things on the moon, but we'd have to bring a lot of things with us to help get that environment just right. I don't believe we've grown anything on the moon yet, but it's something. There are researchers out there who are exploring what kind of plants would be best to grow in space and on the moon to support our crew, and to also produce some of the oxygen that we need.
Thank you. And actually, one of the experiments we've been doing with the school we've been working with recently is actually looking at creating what we call a biodome on the moon. And you can do this at home using basically 2 bottles. I'll post information on our Twitter page after the event. But basically, you get 2 plastic bottles that you cut in half, and you make a sort of a self-contained habitat that you put some soil in and some seeds. And it's basically all you need. It's like you're growing a habitat on the moon. So it's a self-contained dome, a bit like those domes you see at the Eden Project. In fact, they're sort of the same thing, where we make it a habitat that's very different to the one around it. This is what we'll have to do on the moon, because we can't grow things just in the air, as Hannah said, or there isn't enough air to grow on the moon. So they'll make these biodomes, and then we can grow the plants and everything that astronauts might need to survive there. But you can do this at home, creating your own little experiment, and it's really fun to actually see these watercress seeds growing, whatever you put into your soil, and they grow in this little self-contained world. So it's a really fun experiment. I know the school we've been working with, they've just started growing their seeds, and they're all very excited that it's happening and that it actually works. So it's nice to give them a scientific experiment that works, because they don't always. So that's been really fun. So also related to this question, I don't know, Ben, can you tell me, do aliens live on the moon? This is a question from Macy.
Do aliens live on the moon? I would say unfortunately not, or I'm afraid not. And it's not made out of cheese, as Natalie has already stated. So 2 facts that are a bit disappointing, I guess. But it doesn't mean that aliens don't, live somewhere else in the solar system. There are lots of possible places in our solar system that aliens could live, or some sort of biological creature could survive. So there's places like icy moons, or the atmosphere of Venus, for example. So there's lots of cool and weird places in the solar system, and we're only one tiny solar system in a massive universe, so there might be lots of life out there. So not the moon, but maybe somewhere else.
That's really good. And actually, that's really important to point out, I think, because we think we're so important here, don't we? We're like, oh, Earth is so important, humans are so important. But we are just one planet out of 8 in our solar system, and we're just circling around one star, of which there are absolutely billions out there. So actually, that's quite important. We haven't gone to look at all of these stars and all the planets that orbit around them. So we really don't know what's there yet. So we might not be unique. We might not be as special as we think. There might be other animals out there. Ben, what's your favourite moon or planet in our solar system that you think might be the most likely to host life?
So for me, there's an icy moon that orbits Jupiter, and I think it's called, I can't remember the name. It might be Io, it might be something else, but
that'll be Europa.
Europa, that's the one, and it's got like an ice crust, and then underneath there's possibly liquid water. So it's like a planet made out of ice and water, which I think is just really, sort of sci-fi, and there might be some sort of creatures swimming beneath, and I think that's really cool and sci-fi. It's something out of a movie. So I think that would be my favorite.
Yeah, that is a really popular place. I think NASA have a mission actually planned. I think it's planned now to go and actually take a look at this icy moon. And there's others as well. There's another one around Saturn called Enceladus, which is very similar sounding. And actually, it's got this kind of liquid ocean below this icy crust, not dissimilar to what we have here in places. And then it's got this warm rocky core, which is really important. If we want to look for life anywhere else in the solar system, we must look for a planet or a moon that creates its own heat, because we think that's one of the most important things for life. We need to create some kind of energy for that life to survive on. So there's so much still to discover out there. It might be that we go there and we don't find any life, but there is every potential that it could be there. So you never know, in your lifetimes we may still be finding new things about the solar system. It's almost certain that we will. Okay, next question. Let me have a little look. Is the moon big but just far away? And that's from Carson. Who's going to take this one?
So the moon is, yes, so the moon is about, I think it's a bit bigger than Australia and a bit bigger than America. So it is quite big if you think about the scale of it, but it is also quite a distance away from us. It is thousands of kilometers away from us. So it looks a lot smaller from when we look at it. It is actually quite massive. I'd also like to clear up, I misspoke earlier when I was speaking about the age of the moon. I was actually talking about the earliest rock, so the Highlands material on the moon's surface, which we have dated to 4.2 billion years old. The actual moon itself formed around 4.5 billion years ago, so it's almost the same age as the Earth, but it was entirely molten for a very long time. I just thought I wanted to clear that up.
I should have picked that up because I knew that as well. And we get so confused with all the numbers sometimes. But yeah, okay. So the moon actually formed very soon after the Earth formed, around 4.5 billion years. You are correct. Thank you for realising that. We've cleared that up for everyone at home. Let me see. Now, I just very quickly want to take a short break from the questions. I do have more that have come in. I'm very excited to share them. But what I'd like to quickly do, and I can find it in my notes, which is somewhere in here, is that with Cold Harbour School in Milton Keynes that we've been working with, as I've already mentioned, I wanted to share with you one of the poems that they wrote. Now, it's absolutely amazing. So basically, they were doing science and they were learning about the moon. But then we suggested loads of activities that they could do thinking about the moon, but in their literacy lessons or maybe in maths or something like this. So they've been thinking about the moon for 3 weeks. They must be totally immersed in it by now. And the poem I'm going to read you is actually by Ethan, and he's a year 6 student. And the poem was to imagine life on the moon. Because there are actually plans to send send humans back to the moon. And it's going to be the first woman, because we've never sent a woman to the moon, and also the next man. And it's actually going to be in 2024, which is just a few years from now. That's the plans anyway. Now, it sounds crazy because we haven't sent humans there for nearly 50 years since Apollo 17, but we are now planning to go back. I think we'll come back to this in a little bit more because we've got a few questions about it. It's really exciting that we're going back to explore the moon with humans again. But so this is Ethan's poem. Now, if you want to have a go at making your own poem, then please do, imagining life on the moon or what it was like for astronauts that first visited the moon. And if you want to share those with us, then you can email them to us at stem-communications@open.ac.uk. You might prefer to write a short story. I used to love writing short stories when I was younger. And we'd love to hear from you, because we'd love to hear kind of what you're experiencing about what you think the moon would be like. So Ethan's poem is called Living the Lunar Life. Living the lunar life, there is no ocean to see. Living the lunar life, there is no oxygen for me. Living the lunar life in my metal moon buggy. Living the lunar life where the dark side is chilly. Living the lunar life where the sunsets are monthly. Living the lunar life 384,000 kilometres from my family. Living the lunar life where asteroids hit regularly. Living the lunar life, Neil Armstrong got there before me. I just think that's so lovely, and I really wanted to share it all with you. What a lovely poem. Well done, Ethan, and thank you for sharing that with us. It's just so fantastic. So yeah, please do send us your poems, because I'd love to hear more of these, and we'll find a way to share them if we can. Now, Ethan's poem brought me on to one of the next questions I'm going to ask, which is actually about craters on the moon. And one of the questions is, why are there craters on the moon? That's a really good question, because when we look up, we see all these kind of round circles on the moon. And so we might be wondering what they are. Who wants to take this one?
I can take this one.
That would be great, Lucy. Thank you.
So the craters on the moon were formed by lots and lots of meteor impacts, so rocks that fell to the moon and they've impacted the surface and formed these craters. Back in the very, very early history of the solar system, when everything was just forming and getting settled, there was an event called the Late Heavy Bombardment. This is around 3.9 billion years ago. So lots and lots of rocks and debris were flying all around the solar system, and lots of these have impacted the moon. So a lot of the bigger craters that we see on the moon were formed during this event, and that is why they're so big, these huge impacts. But there are obviously things are hitting the moon all the time, a lot of micrometeorites, which are the very, very small ones that we won't be able to see, but that's why the moon is so heavily cratered.
That's brilliant, thank you. Right. A question about the colour of the moon. So this is a really good question. There's two actually related to this. So the first one is, why is the moon grey/silver? And that's obviously how we kind of see it from the Earth. But also someone else has asked, what colour would the moon look like when you're standing on the surface? So yeah, who's going to take this one? I'm thinking we should probably discuss, in terms of the colours with the grey and silver, maybe someone can talk about some of maybe the rock types that are on the moon, because I think this probably relates to kind of the colours that we see. Yeah.
Do you want me to jump in on this one?
That would be great.
Yeah, so the different rock types that we can see, broadly speaking, we've got the very sort of silvery light colours, and then we've got the darker grey colours. Are two different rock types, shall we say. So the darker colours is what we call basalt, which is a volcanic rock. So it formed when the moon, lots of lava erupted from the moon, from the mantle, and filled these craters that I was talking about earlier. So that's why we've got the darker rock. The lighter rock is mostly made out of anorthosite, which is a very special kind of rock that is formed from a mineral called anorthite, which is very complicated geology, you don't need to know probably, but that is why we've got these two distinct different colours that we can see. So the anorthosite is a lot older than the mare basalt, so it's what formed originally, and then the mare basalt has come out and filled these craters since then.
And there's another really interesting material that I really like on the moon, and they're called pyroclastic glasses. And this was something that Harrison Schmidt, the geologist, it caught his eye, whereas all the other astronauts were all pilots and engineers. But he had his eye, and he spotted this material, and it was orange. And he was like, why is that orange material on the moon? And actually, they're able to collect other material as well, which was green. And these are glasses which were released from called pyroclastic eruptions, which is basically just this very erratic release of magma that cools instantly into a glass, and it traps some of the material from deep within the moon. And depending on what that material is, it will change the colours. So those are two other colours that you can see on the moon, but you couldn't see it from a distance. But if you were landed on the surface, that's something that might catch your eye.
And that's a really good point you made there about Harrison Schmidt, because I think at this point in the mission, they were being told by NASA to get back. They had to get back to the lander. And he saw this rock, so the story goes, and he said he absolutely couldn't pass it by, because as a geologist, he'd seen all these grey rocks and everything, and then he spotted something that looked different to him. And he said, I have to sample this rock. So very quickly they stopped. I think they were using the moon buggy, and he sampled some of the rock, and it's actually become, one of the most important samples to come from the moon, because it's allowed us to learn about this part of the history. So it just shows you, in fact, that whilst, we send engineers and pilots to the moon, and often they go into space an awful lot because we need them to fly the spacecraft, but we also need scientists and other people who, think differently and have a different background and have a different experience, that, we can put all these teams together, and then they each do their own little part. So it's really cool that he was able to do that. And we touched on the Mare basalt. So this is another really cool thing. So back in the day, 1700s, when people were looking up at the moon, they actually, like we can see, they saw dark patches and light patches. And the dark patches get their name, the mare, and that's Latin, okay? So it's Latin for seas, basically. It's like oceans. They thought they were seeing bodies of water on the moon when they first looked up. And obviously, they'd never been there, and they didn't have really exciting telescopes like we have today. They couldn't see in detail what was on the moon. They never sent a space mission there. So they could just see it from Earth. And they thought, quite rightly, they were like, we think it looks like the oceans on Earth. But obviously now we've been there, we know that these are these dark basalts, which are very similar to what we find in places like Hawaii or Iceland, other places on Earth that are volcanic in nature. And actually the rocks are really not very different to those rocks that we find on Earth. And then Lucy mentioned the slightly lighter rocks, the anorthosites, and these are called the Highlands because they tend to be slightly higher in elevation, and they are slightly older than the Mare. So we have these two rock types on the moon. We've got the Highlands and the Mare, and then we also have these kind of glass beads that Hannah mentioned. But they are generally kind of grey, darker grey and lighter greys. That is generally the colours on the moon. I think if you were standing on the surface of the moon, they would look the same colour because that's kind of just the colour of the rocks. Okay, who's going to take the next question? We're going to talk about, do electronics work on the moon? That's a good one, because if we're going to go back and explore the moon, we're probably going to need to take quite a lot of equipment with us. So I don't know if Alfie here, again, we've got another Alfie, is asking about kind of the radiation environment on the moon or something like that. Who wants to? Hannah's nodding. Do you?
I mean, I can. I don't mind. So on Earth, we are protected by the atmosphere. So this is the air that's covering this nice little shell around the Earth. And on the moon, there isn't an atmosphere. So there isn't this protective layer. And radiation is constantly being released by the sun. And so without that protection, this radiation can actually damage electronics. And it can also damage humans. So we're actually quite concerned about this radiation. So we're going to have to build protected moon bases. And also, I know there have been ideas of also building like little protection covers for rovers. So if we want to have rovers that are going for a really long time, perhaps we could build like a little hub for it to kind of hide in and protect itself. And it's also one of the reasons why it's been suggested humans could live in lava tubes, which are basically caves on the moon, which is, I think, really cool. So you could have astronauts sort of abseiling down into their base. So yeah, radiation is a really big issue. And if we want to have long missions on the moon, then we really need to consider it and how to protect our equipment.
That's great, thank you. Okay, let me see. I've got a very small font to read on my screen. I'm very sorry. I'm just going to zoom in a bit. Okay, a question from Ben, aged 9. Has anyone explored the dark side of the moon? So as I mentioned, if you maybe you've missed the beginning, but we now call it we tend to call it the far side of the moon, because actually, as we learned, it's not always dark, but a lot of people do still call it the dark side of the moon. So we know what you mean. So has anyone explored the far side of the moon? Who's going to take this one?
So no person has gone to the far side of the moon yet. That is what the upcoming missions by, for example, NASA, the Artemis missions, they are planning to go to the far side of the moon, to the South Pole, as Hannah was talking about in her talk earlier. But we have sent missions to the far side. So we've sent rover missions. The Changi mission has just been to the far side of the moon. The Changi 5 mission, which is on its return, has been to the far side. So we have seen the far side and we have explored the far side, but not in person.
Okay, and why is that? What makes it so hard to go to the far side of the moon? It's obviously further, but you have to orbit around the moon to get there anyway. So what makes it so different to the near side?
So on the far side, there's obviously the issue that we are not directly seeing the Earth. So communication with the Earth takes a lot longer and is a lot more tricky. We've obviously put in place satellites, I think, that allow quicker communication now, but this was not the case in the 1960s and 1970s. So this was not possible at this point.
Okay, thank you. Right, another tiny font for me to read. Here we go. Lately, the Chinese Space Agency has expressed interest in sending missions to the moon to exploit natural resources such as helium-3. This is quite a long question, so be prepared. Whereas NASA seemed to be focusing on conducting scientific expeditions. Which approach do you think would be the most valuable to the human race? And that's from Adam.
Oh, this is a good one, because they're both just as important and they are not exclusive from each other. Helium-3 as a resource, it has been considered before. I think now it's debated whether it's something that is worthwhile sort of using. But there are lots of things that we're looking for on the moon. So we've mentioned water. Just as an example, if we find water on the moon, we can learn a lot about the water cycle on the moon, and also what that means for the water cycle on other planetary bodies. So scientifically, it's interesting, and that's why we want to go there. But it's also useful for exploration purposes and for utilising that resource, mining it to support a moon base. So I find that actually they both support each other, and it's really hard to separate them because they're both really interesting.
Does anyone have anything to add to that? I know Tara's shaking her head. She's like nodding away.
I definitely agree with what Hannah's saying. They're definitely, like, they both complement each other. So we really cannot do one without the other. They will inform each other, and that's why it's useful to do both. And for science to progress, we really should do both.
Brilliant. And luckily, we've got a lot of, different companies involved in space exploration now, which we mentioned. And so that's really opening up things a little bit. Like, we're finding cheaper ways to get mass into space, which is really important when we want to keep on going back to places, because ultimately it's very expensive to send things into space. So, if we can find a good way to do reusable rockets and things like that, that's going to really, really help us. So all the developments that have really happened in the last sort of decade have really brought some of this science forward, and it's going to open it up for people like you who are doing all this lunar research, because hopefully you'll get more samples in the future and learn more about these bodies, which is great. Okay, so I was going to go on to this question that's been sent in, and it says, in which craters or which crater or craters has water been found on the moon? Because you mentioned that, I don't know if you were watching Hannah earlier with her Google Moon tour, she mentioned that we found water in the polar regions on the moon. Do we know which craters specifically have water in?
So I remember there was a mission, I think it was part of the Alcross mission, and they literally released part of the spacecraft, which was kind of not in use anymore, and basically fired it into the South Pole, and just to see what was released. And I believe it was the Cabeus crater. but I could be wrong here, so please jump in if I am. And in the plume that was ejected, the orbiting spacecraft actually detected water molecules. So that's kind of the only direct sort of sample that we have, but we haven't landed in there yet. But there are plenty of pieces of evidence that tells us that there's water in a lot of these craters. But I believe, Cabeus is definitely, Mahesh is correcting me. Cabeus crater. It's all good.
Excellent. Well done. It's like your PhD examination all over again.
I
know. Okay, and what's the largest crater on the moon? Do we know? Have we measured them all, and do we know which is the largest crater? That's another question that's come in, actually.
So the largest crater is actually the South Pole Aitken Basin that Hannah was talking about earlier, that was so large it managed to actually expose the inside of the moon to space. So it was a catastrophic impact and so massive. I do not have the exact number, but it's
2,500 kilometers-ish, I think.
There we go.
Wow. Okay. So this was a massive piece of asteroid or something, we think, that kind of impacted the moon. Do we know when that happened?
Not sure.
I'll put everyone on the spot there. We might have to Google that for you. You can Google it at home. So so this was, I think it was quite early in the moon's history, wasn't it, that we think this happened?
It was. Yeah. It was just after the crust formed, I believe.
So just after the Highlands kind of made, the anorthosites made themselves. And okay, so that's good. It's not a question that's come in, but it's a question I think it would be quite an interesting one for someone to answer. And it's actually how we use the craters on the moon to figure out how old the surfaces are. Anybody want to jump in? Or have I asked a question to myself?
So we can use the craters to chronologically map the surface. So if you've got a big crater and then lots of little craters inside that big crater, you know that the little craters inside are younger because they happened afterwards. So we can kind of piece together. It's not an exact science. We don't have samples from all regions of the moon, so we can't say exactly how old things are, but we can at least make kind of a geological map, if you like, of the age of the surfaces based on these craters and how they interact together in their relationships.
So it's actually called crater counting, isn't it? And it's quite simple. I mean, scientists get, images of regions of the moon, and then they count the number of craters that they can see and the sizes of those craters. And if you have a lot of craters in one area, what this tends to suggest is that region is quite old, because it means it's had time to accumulate a lot of impacts from space. Whereas if we go to some younger region, maybe somewhere that's been volcanic and has just kind of splurged out a load of volcanic material onto the surface, what we'll find is that it doesn't have many craters because it hasn't had time to accumulate those from space. So when we look at planet Earth, for example, many of you will understand that we have plate tectonics here, which renews our surface all the time. We have plates that move and destroy our crust and make new crust with volcanoes. So we don't see many craters on our surface. We only have a couple really that we can notice, even if you look from space. Whereas when you look at the moon, it didn't have plate tectonics. So actually the surfaces of the moon that we see are all very, very old in comparison to our own planet. But it means that we can use the moon to actually learn more about Earth, because we can see back into the history that is no longer preserved on our own planet. So the moon is really, really useful. Actually, in general, space exploration can be really handy for learning more about our own planet. We can look at other planets and moons and discover kind of what was going on in their history, and therefore kind of what we're missing, because we only see the last kind of about 1 billion years on Earth, really. There's some really kind of older sections on Earth, but most of it is not particularly old compared to, say, the moon. So yeah, crater counting is really, really important. But then what we can do is go to the moon and sample some of the rocks from those regions, and then we can give it a real age. We don't just say, oh, this region is old or older than this region. We can put a real dated age on it of 4 billion years or whatever it might be. So there's lots of very detailed science that has to be done to try and understand all the features that we see.
Can I just jump in there, Natalie, as well?
Yeah, go ahead.
There's a question in the chat that ties in quite well with this. So Lucas has asked, how do the footprints stay on the moon? And that is to do with also the craters. And if we look at the Earth, we've got lots of running water, we've got an atmosphere, so there's lots of erosion, lots of things are breaking down the rocks all the time. So that's another reason why we don't see things preserved in the Earth nearly as well as we do on the Moon, where there's no running water, there's no atmosphere. So these things aren't being destroyed, they're not being changed. The only thing that's changing the surface of the Moon really is these meteorite impacts that will mix the soil. But other than that, there's no erosion. So everything stays exactly as it is, really. That's why we can see so many craters.
So if we went back to the Moon, tomorrow, and we went to those same places, we would still see the footprints, wouldn't we?
If they haven't been hit by a meteorite, then yeah.
That's very cool. That would be very exciting. Right, let's do a space travel question now. From Ollie, how long does it take to get to the Moon? That's a great question. I get this question all the time, actually, because people don't really know. That's great. Who wants this one? Go on, Ben.
I could do that one. I think to get to the Moon, it takes about 3 days. So it's not actually as long as you think. Well, to me, I would have expected it to be much longer, but it's only 3 days to get to the Moon because you're traveling so fast. Whereas Mars, which is a lot further away, is about in between 6 to 8 months or so. So there's a big difference in distance.
And what's interesting about that, when you say you're traveling really fast, Ben, is that it's really hard to imagine just how fast these crew are flying through space. I believe it's something on the order of, the speed of a bullet. So imagine a bullet going for 3 days. That's kind of a way to kind of visualize just how far away it is. It's just our technology is really quite cool that can get us there that quickly.
That's really cool. And then I guess when we're thinking about getting to Mars, we're talking about, in the future, actually having the Moon as a base for humans to then travel onto Mars. What's the advantage of doing that?
I can do that as well. So the Moon has very, very little gravity. So taking off from the Moon would take a lot less fuel and energy because you've got no gravity and no atmosphere. And that's like I think that's probably the main reason. And with having a lunar bases, like we were talking about earlier, is that you could get possible hydrogen and then turn it into fuel. So then you wouldn't have to bring the fuel with you to the Moon. You can just make it there and then fly off. So just cut the time a bit and make there less fuel to be used.
Okay, yeah, that's brilliant, because our gravity is a bit of a problem. Whilst we rely on it, it makes it very expensive to launch things off our planet. So actually going to the Moon, I think it's just 1/6 of the gravity, and that's just because it's a smaller object. It's got less gravity. It makes it a little bit cheaper for us to do it. But actually related to this is a really good question. It's from Matt, again with the tiny font, sorry. How did they get the Moon Rover to the Moon, considering the lunar module wasn't very big? And I think that's a great question, because I don't know the answer.
I have no idea.
Was it taken in pieces? This is something I've never even thought about.
So I can't answer that question, but I've got one of my favourite facts about the Moon Rover is that when they used it, so they have rear fenders. Well, they have fenders on above the wheels to stop the dust kicking up. And again, because there's low gravity, that you get quite big dust clouds that are really quite annoying. And one of these fenders got broken off, and it caused a nightmare for the crew who were driving, because they were just creating this mess everywhere. And so they actually took one of their maps that they created for the Moon and basically duct taped it onto the back to try and create some mock fender to stop the dust coming up. So I think it was folded up. Yeah, so on the chat they're talking now that the Moon buggy was folded up, but it apparently is quite fragile as well.
So it's a foldable moon buggy. That is amazing. Actually, one of the projects that we were doing with the local school, they actually are now going on to make their own moon buggies. So actually, I bet they haven't thought about this. I might, if they're not watching now, I might remind them actually that they might want to try and think about a foldable moon buggy. That's another step of complications that you've got to add to it. And actually, that's quite important when we're thinking about putting humans on the moon again. So we've obviously done it. We've sent lots of things up to the moon. But what are some of the challenges for getting humans and keeping humans on the moon? How are we going to get all that equipment up there to support them? I know Hannah can probably answer this one, or whoever wants to do it.
Okay, I can jump in, but please jump in if you have answers. So at the moment, like we were saying earlier, the gravity on Earth is quite limiting. So we have to build massive rockets to get us up there. We had the Saturn V rocket, which is 100 meters long, and that was to get 3 crew members to the moon. Now imagine you have bigger teams, you've got all the equipment and all the moon bases. That's looking like a lot of launches, which is very expensive. So hopefully we want to get the crew there, and we'll likely be sending missions before the humans get there to kind of get the supplies that we need. So we might have, we could, for example, put machines down that are going to generate all the water that we need, or we can send rovers that 3D print roads and habitats for us, so we don't have to bring everything with us all the time. But I remember there was a really interesting fact of how so our spacecraft that we launch are limited by the size of the rockets, and the rocket, I think it was the solid rocket boosters, were limited by the size of the train tracks that had to transport them there. And the train tracks are predetermined, the distance of the tracks is determined by the chariots that used to ride around. So it's weird how our spacecraft is limited by the size of the chariots that were being designed by, people hundreds of years ago, and how that's all interlinked. Yeah.
And actually, it goes one step further, because the chariot sizes were actually determined by the size of a horse. So actually, you could argue that it's the size of the horse that's then determined the size of these space exploration vehicles. It's quite crazy. I should probably point out my dad, who's probably watching. I remember him telling me that when I was much younger, and he loved that fact. So I'll shout out to my dad, because I've remembered that all my life. Look, we're nearly coming to a close for the live Q&A. I can't believe how quickly this has gone. We've got through so many questions. I actually have another question for you at home, which hopefully is going to come up on the screen shortly. Mahesh is going to come back and answer this question after we see Hannah's tour to the moon again using Google Moon. The question I'm going to ask you is basically, the gravity on the moon is stronger than on Earth. True or false? Okay, so is the gravity on the moon stronger than on Earth? So that's your question. Have a little think. We've probably addressed that question already, so hopefully you will actually already know the answer. So stay tuned. Mahesh will be back in about half an hour to reveal the answer. But I'm afraid that is all the questions we have time for today. If you have more questions, please do send them to us at stem-communications@open.ac.uk. We will either email you back if we get loads and loads of questions in. That may be too much to ask of us before Christmas. I will try and put a lot of the questions on Twitter or on our website, so do check back if you've got anything that needs answering. Now, in case you missed it earlier, you have another chance now to join Dr. Hannah Sargent for a virtual trip to the moon. You've been hearing a lot from her recently in the last hour. She's going to take us on a tour of Google Moon again, and learn basically some more lunar science and exploration, and learn more about some of the things you've been hearing about today. But maybe you're also free tomorrow or Wednesday night, when we have 2 more Moon Night events. Now, these are primarily aimed at children and families, but you might still be interested to come along. Tomorrow we have a talk by Dr. Jessica Barnes, and she's zooming in from Arizona. She's going to talk to us about water on the moon, of which we've heard a little bit about tonight. And on Wednesday, we have the 6th annual Colin Pillinger Memorial event with a talk by Dr. Andy Spry about planetary protection, which is a really important subject we're thinking about as scientists now. It's also followed by a Q&A. Now, you can find more information about these events on the OU STEM website, and a recording of all of these events will be available also probably on Facebook and our YouTube channels shortly. Thank you so much for joining us for this live Q&A. I've really enjoyed it. I've had so much fun trying to get through these answers, some of which we were a bit stumped by, I have to be honest, but such great questions. I'm going to get the team here to wave and say goodbye to you all. Thank you so much for joining us, and I'm going to hand back over to Hannah now. Thanks, everyone.
Thank you, Natalie. Yes, so once again, we have another quick review of the walkthrough of how to explore the moon from the comfort of your own home. So these are some free to use software that you can easily access. And I'll be talking about some of the Apollo missions and how you can explore them, and also how we're using updated maps and images to help and guide us as we plan our future missions to the moon. Enjoy. Okay, so to begin with, I'm going to be looking at Google Earth and an aspect of that called Google Moon. Now, many of you might be familiar with Google Earth. You can access it on your internet browser, or you can actually download for free something called Google Earth Pro, which is what I'm going to be using today. I just find it easier to work with. So if you go to this is just the opening screen of Google Earth Pro, and if you look to the top bar here, you might notice there's a small icon in the shape of a planet, and if you click on that, you can scroll down to Moon, and that will take you to Google Moon. Now, Google Moon was created about 10 years ago now to celebrate the 40th anniversary of the Apollo 11 landings. So Google Moon uses imagery from Clementine, and this took images of the moon in orbit, and that's why we have these stripy images, because as the satellite was moving up and around and across the surface of the moon, and around the moon, the lighting would have changed slightly throughout the days, and that's why you have these different sort of stripy artifacts of these images. And this is the face of the moon that you might be used to seeing. So this side of the moon, called the near side, is always facing Earth. So when you look up into the night sky, this is the side of the moon that we always see. So you might be used to seeing some darker areas and some lighter areas. So the lighter areas, we call them the Highlands. These are older materials formed when the moon initially, when it was sort of molten rock, when it was initially cooled down. This is some of the first material to cool. But then in the lower areas, these actually flooded with lava in these oceans of lava, and forming this basaltic darker rock. And actually we call them the mare regions, which translates to seas, because ancient astronomers actually thought that these were seas on the moon. But what's interesting, if we turn the moon around, this is what we call the far side of the moon. So very few people will have seen this with their own eyes. Only the astronauts that have orbited around the moon will have seen this side of the moon themselves. And you can see it's very different, actually. It's a lot of lighter material, so a lot of highlands on the far side of the moon. And it's not called the dark side, so that's a common misconception, because the far side of the moon also sees sunlight. And that's why we were able to take these lovely images across the surface of the moon. Okay, so let's scroll back around here also. Okay, now one of the main reasons I like to use Google Moon is because it's good for looking back in history and human exploration, particularly during the Apollo missions and so on. So, for example, let's take a look at some historic maps. So on the left-hand side down here, if I click on historic maps, so these are maps that were created around the time of the Apollo missions to help support the missions. So we have some geologic charts here, and they're split up, I believe they're called quadrangles. So each map would have, just to break it down into sort of bite-sized chunks. And if you click on it and zoom in, oh, sorry. See if I can click on one of these. There we go. Explore this map. So you can actually look at the original map that was created. And if you use your scroll wheel on your mouse, I would suggest using a mouse for these. I just find it easier to work with. So these are some pretty old maps here. This one was created in 1960, in fact. So this would have been using images of the moon, and they would have looked at the different shades on the surface and the shapes that they could see and try and determine what sort of materials they are. And again, you can look further at those over there. But more importantly, these maps are used to help determine safe landing sites as well. So you can use the geologic maps to help find areas of particular interest, where we might want to collect some samples to bring back and study here on Earth. We also have topographic charts. So these are charts that tell you about how steep slopes are, and what the terrain is like. And this is helpful for finding your safe landing site, because you want to land somewhere nice and flat. It's really hard to pinpoint an exact place where you're going to land, so you need to have a big wide open space, a flat space that is safe for the astronauts to land in. Okay, so I'll close off of this historic chart. Now you might also notice these small red flags, and those little red flags are human artifacts. So these are things on the moon that were created by humans, and we also have the Apollo mission. So what I'm going to do, I'm going to take us in to Apollo 11. So I'm just going to click on the Apollo 11 badge here, and it will take us all the way in. So you don't need to know where exactly the missions went, because Google Moon will do it for you. Okay, so what we've got here is the landing site of Apollo 11. Overlaid on top is one of the maps that was created showing where the astronauts went. So you can see they didn't explore too far away from their landing site. Just a couple of little craters nearby, nice and close to their lander. So if you zoom in, so I'm just going to scroll in here, you can see they've superimposed the lander. Let's see if I can turn around. So we have our lander here, we have a flag here, and you can see there's lots of little things you can click on. So there are some YouTube videos that you can go and check out, of videos that were recorded on the surface. We can see exactly where things were placed. So we have SWC, this is our solar wind collector. And we can also check out some cool images that were taken on the surface. So if I go the view from Little West Crater, fly to this photo. So this was taken by one of the astronauts. You can see we've got the lander here. There's our solar wind collector. This is one of the science experiments. Got the nice shadow of the astronaut there. And this is one of the craters near to the landing site. Okay, so if I zoom out, so there's lots to explore here, lots of like cool little artifacts to go and check out. But now I want to take us on to Apollo 17. So this is the last mission from the Apollo era. So these are going to be the last humans on the moon, and we can see how different the missions were. So I'm going to fly us in to the Apollo 17 landing site. Okay, and you can see, so we've got superimposed here the route that the astronauts took, and so they had a rover this time so they could go and drive around and explore, and you can see they explored much further away from their landing site than they did in the first mission to the moon in Apollo 11. Now what I'm going to do, one of the cool features they have here, they have some guided tours from the astronauts, so you can listen to Buzz Aldrin talk about Apollo 11. I'm going to give you a quick snippet of the Harrison Schmidt guided tour. So Harrison Schmidt was the only scientist to have ever gone to the moon. Everyone else, they were, your pilots, the standard astronaut of the day. Whereas having a scientist, particularly a geologist, is really helpful because they can pinpoint areas of interest or particular samples on the surface with their eyes that we might not have thought about or identified from orbital images. So let's have a quick listen to this tour.
I'm Jack. Apollo 7 just flew on the Apollo 17 mission in December of 1972. The crew of Apollo 17 was an aggregate of two backup crews, Apollo 14 and 15. I replaced Joe Engle on that crew, and Gene Cernan would be the commander, and Ron Evans was going to continue as the command module pilot. Gene Cernan got out of the spacecraft first, and I followed him fairly quickly afterwards. We were in a valley deeper than the Grand Canyon of the Colorado. The mountains on either side were 2,100 meters, or about 7,000 feet high. The sun was as brilliant as any sun that you can imagine. Even more impressive was the Earth, which was hanging over one of the mountains and stayed hanging over that mountain, the South Massif. And that was really a magnificent sight for me, and that's what I remember as being sort of my first real impressions of the Valley of Taurus Littrow.
Okay, so there's plenty more for you to check out there. I'm just going to exit this ground level view, and I want to take us to one of the places they visited. So they visited the base of this mountain here, the South Massif. And you can see that the images, the problem with the Clementine images is that they are outdated now. We do have much more improved imagery, so there isn't a lot of resolution here. But I do like that they have superimposed some images taken at these locations that you can go and zoom in on. Let's see. Fly into this photo here. So this is at the base of the North Massif. There's another of the crew members there, likely taking some samples. Oh no, sorry, taking photos and images by the looks of things, and videos. There's the rover down there. You can see their footsteps in the sand, well, in the soil, shall I say. Okay, so I'm just going to zoom out of this now. So what I'd like to do next is look at this same location, but using a different piece of software or program that you can all have access to. Okay, so next I want to take you to use another piece of free software. Well, it's a program that is available online, and it's called Elbrock Quick Map. So if you search into your search bar, Elbrock Quick Map, this is what should come up. Okay, so Elbrock Quick Map is actually, it was designed for the Lunar Reconnaissance Orbiter camera team. So the Lunar Reconnaissance Orbiter is actually in orbit still around the moon, taking lots of images using all of the different cameras, and also obtaining lots of different information using other instruments they have on board. But the team wanted to be able to see their images as one on the moon and look at kind of like how they refer to each other and kind of like the context within the whole moon. And so they worked with ACT to develop this program, and most importantly, they made it free to use for everyone, which has been great for people like me I've actually used this in previous research, but even just for lunar enthusiasts who want to go and explore the moon and looking at some of the most recent images and data that we have available. So first off, it shows you this 2D version of the moon, but it can see it's beautiful and crisp. I find a lot easier to look at than the Google Moon version, and you can actually switch to 3D and take a look again all over the moon, and it is just, well, I find stunning. Anyway, so I'm going to return us back to the home view, and I want to fly us in to the Apollo 17 landing site again. So it's actually been around 48 years, almost I think to the week, since the Apollo 17 mission, which is one of the reasons why I'm really interested in taking a look at this site again. And we can take a look at this site. So first off, how do we find it? It can be a bit overwhelming, so there are a lot of different options here of layers of things to search for, but I'll try and walk you through it gently. So if we go to overlays, and we can click on anthropogenic features. That's just a fancy way of saying human artifacts. So things that humans have created that are now on the moon, whether that's landers or rovers or debris or whatever it is. And if you click on the text underneath, you should see there's a lot more information and directions of where to find more information. And we can actually narrow down the particular feature that we're interested in. So I'm going to look for Apollo 17, but you'll see that there are lots of other missions highlighted here from lots of different countries as well, which is really important. So first off, I'm just going to take a look at Apollo 17. So I want to head to the lunar module. It takes us right in, which is perfect. Okay, so I just want to check. Okay, so I'm currently in 3D, but for what I'm about to do, I want to be just on the near side projection. Okay, so it doesn't work as well with 3D. And what I want to do, if I zoom in here, okay, I want to now draw a shape around the Apollo 17 landing site and search for the best high resolution images we can find. So I'm going to draw a polygon, just a shape around here, double click to finish, and I'm going to search for, again, lots of different data sets you could look at, but I'm interested in the narrow angle camera. So this is the highest resolution images that we can look at, but it will give you a lot of, it will just kind of, your screen will freak out. So we want to filter it down. There are lots of things you can look at, but for what we're doing here, the only thing of importance is resolution. So you want to have the smallest amount of space per pixel. So I want to go less than a meter per pixel. Okay, and just I'll click on the first one that comes up and it will load, and look at that. So if I zoom in, I think this is the maximum I can zoom in. So this here is the lander, so it's still there. What's left of the lander. On the moon, we've got the little shadow created from the lander, and then you can see all of these marks from where the crew in their rover went and explored. So these are images that have been taken from the Lunar Reconnaissance Orbiter every time it flies over the Apollo 17 landing site. So these are taken at different times of day. So no claims of we haven't landed on the moon before here. So we've got all of our lovely images here from the Apollo 17 landing site, lovely and crisp and really beautiful to look at. But next I want to take us back to, so if you remember, we were looking at, or the team went to explore the North Massif, which is this area here. So they explored up to this region. And if we zoom in, even with the wide angle camera, which is what these base images are here, the resolution is so incredible, even compared to the Clementine images. You can see these boulder tracks of boulders that have rolled down the slopes of the moon, and these are created when rock is broken off or rejected from craters, from impacts, meteorites striking the surface and so on. And so quite often we find these boulder tracks down slopes on the moon, and the Apollo 17 crew actually went and visited one of these boulder tracks. And what I'll do is what I'll show you here. I'll try and superimpose it. Oh, go on, I'll have a look. Brief look at this particular boulder. NAC images. Let's go to high resolution. There we go. So you can see that this boulder was actually broken in half. It stopped rolling and it had fractured and crumbled. And the crew visited this site, and you can see these little dark squiggles right next to the boulder, and this is where the crew were walking around and taking pictures, and the rover actually pulled up quite close, I believe. So we actually have a picture of the crew that was taken right next to this boulder. And in the work that I've been doing in the past, we've actually been looking at boulder tracks on the moon, and we can use these images. So we've used Quick Map to measure the size of the boulders, the size of the tracks and the shadows within the tracks to try and understand how deep they are. And we can use that to better understand how soft the surface material is. And if we can do that at locations that we haven't visited on the moon before, and make sure that any rovers that we send there aren't just going to sink into the soil irretrievably. So it's really important that we can use these images for free to do some really important science. Okay, so let's exit out of here. Let's delete these. So now I just want to show you one of the features of Quick Map that I really enjoy, and that is looking at the moon in 3D. Now, because they have some of the highest resolution images and the most up-to-date topography maps, so that again, I mentioned earlier, they are, you know, the slopes that you see on the moon, on the hills and in the craters. And what they've done is they've overlaid them together. So in 3D mode, you can explore them with sort of an astronaut's viewpoint. So if we just briefly switch our projection to 3D mode, it can take some time for the images to load, because it is it's a lot of information that it's now handling. Let's see. There we go. So you can zoom in and out, but if you hold down the mouse wheel, you can take a look. So this is what the astronauts would have seen as they would have descended towards the surface of the moon. So as they were flying in, they would have had to make sure that they landed safely in a nice flat area. And you can zoom in and take a look. So if you were to explore at the base of the mountains, this is what you would see. And looking behind you over here, and eventually the images to catch up. And this is a really useful tool if this sort of program can be used to help train astronauts as they plan their routes as they go and collect samples and do experiments on the moon. Okay, so now I'm just going to exit out of this. So some of you might be aware that very recently, let's go back to the 3D view. So very recently there was a Chinese mission to the moon, and this will be only the third country to get samples from the moon and bring them home again. So this is going to be a robotic mission. It's the Chang'e 5 mission. And it's heading to a northwest region of the moon, somewhere up here, and they're going to be collecting samples and bringing them home. And one of the reasons why they're interested in this particular area is because it's long been thought that volcanism on the moon, so volcanic activity, kind of died out quite early on in the moon's history. But there's reason to believe that there's some much younger material here, suggesting that volcanic activity perhaps went on even longer than we originally thought, and that opens up a lot of questions for the scientists trying to understand the moon's formation and what's been going on in the history of the moon. So that's one really exciting thing about the mission. But also, by sending missions to the moon and getting them safely home again, that's one step closer to sending humans to the moon and getting them safely home again. So a lot of this work is building up to having humans on the moon once again, but hopefully for a longer period of time. Now, next up, I want to take us to the south pole of the moon, because this is where the future of lunar exploration is really looking like it's going to be. So in the south pole of the moon, there's reason to believe, if it's on 3D it gets a bit messy, there's reason to believe that there's frozen water there, and that is going to be a very critical resource. I will talk a little bit more about that in a moment. But first off, I want to take us to Schrodinger Crater. So Schrodinger Crater, let's go to a south pole projection. So Schrodinger Crater is in a really interesting location, which makes it an interesting target for future missions, for both science and exploration. Now, Schrodinger Crater lies near to what we call the South Pole Aitken Basin, which is in this region down here. And in the South Pole Aitken Basin, there was a giant impact that released material from deep within the moon and ejected it onto the surface, including probably in Schrodinger Crater. So if we can sample some of those materials, we can learn about what the interior of the moon is made of. Now, Schrodinger Crater itself is also quite a large crater, so big that it has an inner ring. So you'll see these sort of inner rings form in quite large craters. And this is material, again, that has been kind of risen up from an impact. And we can sample that and learn more about the types of materials found on the moon. But also you might have noticed this quite dark area here, and this is what we call a pyroclastic vent. And pyroclastic vents are quite cool because these are vents where hot magma has basically exploded out of this vent and it's instantly cooled into a glass. But if we can sample that glass, trapped inside could be some of the gases that is found in the material deeper within the moon. So we don't have to dig into the moon, we can just target these areas and it will tell us a lot about places that we can't access much deeper down. And one final thing of interest about Schrodinger is that because it's so close to the South Pole, the sun is very low in the sky, and when that happens you get quite large shadows, and in some places, no matter what time of day or time of year, there are shadows that are, well, they're constantly shadowed. There are areas that are constantly dark and cold, and what that means is that they could trap water ice because it will just stick there and instantly freeze, whereas anywhere else on the moon, water will instantly vaporize. So there are some areas, we call them permanently shadowed regions or PSRs, and these are a massive target for the future of lunar exploration. So Schrodinger could be a really interesting target, but it's still a bit far out from directly over the South Pole, and I'll kind of show you a bit more about that now. So if I go to layers, I want to look at permanently shadowed regions. So this is highlighted areas that I was just mentioning in permanent shadow. But these are, if I look at some of the information, 10 kilometers squared or larger. So these are massive permanently shadowed regions. So there are going to be some in Schrodinger as well. But there could perhaps be better targets in these larger areas here. So these kind of orange outlines were calculated looking at the slopes of the craters and the angle of the sun in the sky, and basically figuring out where there were areas that wouldn't get to see sunlight. But we can actually look at lots of different data sets from different missions and see why we're so confident that there's going to be water ice in these places. So there are areas that we know are going to be in shadow. Okay, so that's the first step. But next we can look at the diviner instrument. So this is looking at temperatures. So if I look at the minimum temperature, okay, and overlay that, what I'm just going to do, I'm just going to blend it in a bit so we can see. And you'll see that in these areas that we think are in permanent shadow, they tend to be the places that are really cold. In fact, some of these places are as low as 30 Kelvin. That's around minus 240 degrees C. And this is some of the coldest places in the solar system. So even though we can't have liquid water on the moon because there's no atmosphere to keep it, to stop it from vaporizing, any water that is brought, if it reaches one of these cold traps, it will instantly stick there. So over millions, billions of years, these could be places that have collected quite a lot of water that we could potentially harvest. So next up, let's take a look at, I think it's the LEND instrument. So this is using a neutron detector. It was able to detect hydrogen that we think is in the form of water. So the resolution isn't great. Let me just turn this down. But you can see over particularly these big PSRs, there seems to be quite an increase in the amount of hydrogen, which is telling us that there's probably water or surface water in these regions. So this is why over the next few years you might be seeing a lot of missions heading to the South Pole, because what we want to do is prove, because we haven't actually been there yet, is sample it and see if there is actually water there. And actually that's some of the missions that I'm involved in. So the PROSPER instrument is being developed at the Open University, and it's going to be landing near to one of these, hopefully near to one of these permanently shadowed regions, and drilling down into the surface and seeing how much water we think we can find there. And hopefully you'll start to see, maybe in our lifetime, permanent moon bases on the moon near to some of these PSRs, hopefully again in a flat area, because we need to be nice and safe, and utilising that frozen water to keep our astronauts alive, but also to convert that water into hydrogen and oxygen, which is our rocket fuel. So perhaps that could get our astronauts back off the surface and return them home to Earth, or even sending missions onwards to Mars. So there is a lot going on, and so yeah, keep an eye on future missions, even starting as soon as next year, in fact. Now there is so much more that you can explore with this program, and I could spend hours going over it. But what I would suggest is, if you scroll down to the bottom of the screen, there's a question mark, and if you click on that and go to Lunar Examples, it will take you to another link here. And the team have spent some time showing you lots of different things that you can explore. Even just straight away here, explore Apollo 12. You can see this phenomenal image here taken at the Apollo 12 landing site. You can also chase the satellite. So this is quite a nice little demo. Quite easy. You can see where the satellite is today, and see what it's flying over and what it's taking images of. And there's just so much more you can play around with. So you could even, as a demo here, this one's slightly more complex, but you can plan your moon base. So what you do is you look at all the different the data sets and see how they combine together, and you can find places that have water, that have flat places to safely land, and multiple different scientific places of interest. And yeah, there's just plenty for you to go and explore. So I'd highly recommend if you spend some time playing around on here.
Hello everyone, welcome back. So those of you who haven't met me yet, my name is Mahesh Anand, and I'm a professor here at the Open University. Earlier today, you heard from my colleagues and team of lunar researchers all about the moon. They answered many of your questions, and I was blown away, really, with all the questions that you actually posed. But also, we actually asked you a question, whether the gravity on the moon is stronger than it is on Earth. And I think Ben might have given away the answer during his response to one of the questions. And if you haven't yet already got it, the answer is that the gravity on the moon is actually less than that on the Earth, which means that the statement we posed was false. And you may have actually come across some videos on YouTube and elsewhere where you might have seen astronauts who visited the moon during Apollo jumping on the moon, and they seemed like as if they were almost about to float. And that is because the moon has one-sixth of the gravity that of the Earth. So which means that if something that weighs 60 kilograms here on Earth would only weigh 10 kilograms. And that's why if you were to actually visit the moon, you would easily jump quite high on the moon. And that's why you see astronauts almost floating above the moon's surface. So that was the question. What I wanted to actually mention before we close tonight's event is, some of these engagements are so much of a learning exercise, because sometimes it doesn't matter how well you prepare yourself, how much you know about something, you always find something new. And that's what I found today, that some of the questions that actually were asked and posed, they made many of us think, and we are still thinking about those. And if you feel that actually your question wasn't answered, or if we answered your question and perhaps not to your satisfaction, there is always more to be found out. So please do reach out to us for any questions that you may have, or you go and look out for the resources which are available on the internet. And we do hope that actually you will return to the Moon Night next year. And hope that you found today's event interesting, and hopefully it has actually increased your curiosity in finding more about the moon and the natural world around yourself. So I think that's all we have for tonight. And before we go, I would like to thank all of my colleagues and team members who presented the activities, all the colleagues who actually have been supporting us from behind the scenes to make this happen. So we can reach you through the information technology. And just before I go, I would like to again remind you that there are 2 more events lined up as part of Moon Night 2020. One happening tomorrow as a lecture, Institute of Physics lecture, taking place tomorrow at 7:30 p.m. And we will have our ex-PhD student, Dr. Jessica Barnes, who will be joining us from University of Arizona. And then the following day, on 9th of December, we will have 6th annual Colin Pillinger Memorial Lecture, where we will have a guest speaker telling us about why planetary protection matters. So hope that you will be able to join us, both events or one event, or you might be able to catch up later on by watching them once they are available as a recorded event. So that's all, folks. Thanks again for joining us, and take care. See you next year.